Hello everybody, Root Beer here with question number 10 on the Euclid math contest paper from the year 2001. Now, if you're just joining me, this is the last question on the contest, so feel free to browse some of the previous videos where I go through all the other questions on the contest. And of course, if you would like a copy to try for yourself before you watch these videos, click the link in the description. It'll take you to the CEMC website. CEMC is these are the people who make and put out these contests. So you can get a copy of this contest for yourself to try on your own before you really watch any of these videos. I know some people just join for the last question because it's the hardest one. And hopefully this question number 10 won't disappoint. It shouldn't. They usually don't. Question 10 is usually a nice, good, solid, challenging question. So let's take a look at question number 10. Alright, so points P and Q are located inside the square ABCD, so we have our picture over here, there's P and Q, such that DP is parallel to QB, and DP is equal to QB is equal to PQ. So we have these lines there, they're the little hash marks, or the dash marks through them to show that they are all the same length. Determine the minimum possible value for angle ADP. Okay. So one of the things I'm noticing right away is because DP is parallel to QB, angle ADP and angle CBQ are going to have to be equal. And so I'm pretty sure that if you rotate this this square here by 180 degrees, you'll actually get the same picture. So I think there's a degree of symmetry in here. So I'm going to see if I can draw a picture of that and see what I can get from there. I'm thinking we're probably going to have to put coordinates on here. Just because minimum possible value, we're going to want to actually make an actual angle calculation at some point. So we'll probably use the sine law or the cosine law or something at some point to get that angle ADP. And so we're going to need values anyway. And if you're going to add values to a picture like this, it makes sense just to add them on an actual grid and give everything coordinates, not just lengths. At worst, you have some extra coordinates to keep track of. At best, you can start using things like the distance formulas and other things like that to make your calculations a lot easier. So always a good idea to put coordinates on if you're going to add in lengths, arbitrary lengths, to a question like this. And because I'm pretty sure there's some symmetry here, I'm going to make the center of the square 0, 0. And so that should help P and Q have similar looking coordinates. So let's see what we can get here. So we're going to make the where on earth is my pen? There we go. So we're going to draw our picture here. Our nice big square. And I'm going to make sure the center is 0, 0. So P looks like it's up here. Q looks like it's down here. And it looks like PQ, just based on symmetry, is going to pass through our center 0, 0. That's awful. You know what? I'm going to draw PQ first, and then I'm going to place the center. Because I'm not having fun passing through those 3 points. So there's P, put Q down here, and we'll connect the two, and there the center will say 0, 0. And we need some, well, let's say that our coordinates are 1, 1, 1, negative 1. So the nice thing here is with the center of the square being at 0, 0, all these coordinates are going to sort of have very similar patterns. So we have a side length of 2 here. So there's some symmetry in our coordinates here. Okay. So we want that angle. We'll call it theta. We'll call it ADP theta. There's A up here, B, C, and D down here. So we'll let angle ADP equal theta. So we're going to make the center of the square 0, 0. Now, since PD, we are told it's parallel to QB, we see angle CBQ is also theta. And let's give P some coordinates, let's say XY. Then Q is going to, so we have coordinates XY here. Q will have to have coordinates, well, we'll need to rotate by 180 degrees. So minus X and minus Y. Alright, let's just double check that in our heads. Yeah, that makes sense. Okay. I'm just thinking what happens to A when I rotate it all the way 180 degrees to C, and the sign's flipped there. Okay. Do they flip and change position? No. Imagine something on the x-axis at 1, 0, which is right here. That'll move down to this point, so it'll become negative 1, 0. Okay, so yeah. So negative x, negative y. All right. So we know that we got some equal lengths here. And thanks to coordinates, we can use the distance formula. So we know PD has the same length as PQ. So let's use the distance formula. So dP is, so we want that length, it's the square root of the difference in the x coordinates, so that's x minus negative 1 all squared, plus y minus negative 1 all squared. So that's the square root of x plus 1 squared plus y plus 1 squared. I don't think I need to expand those out. And what about PQ? Well, again, square root of the difference in the x coordinates squared, so x minus negative x, plus the difference in the y coordinates squared. So square root of 2x all squared plus 2y all squared. And I know these are going to be equal, so I'll square both sides, and we'll get some stuff involving some x's and some y's. Probably won't be a nice simple equation, but maybe we'll be able to solve for, maybe we'll be able to use another piece of information and solve for x or for y. So PD is equal to PQ, so that means PD squared is equal to PQ squared. So x plus 1 squared plus y plus 1 squared is equal to 2x squared plus 2y squared. I'm going to at least expand this out to 4x squared plus 4y squared. Okay, and I guess if I'm expanding those out, let's expand these ones out as well. So that's x squared plus 2x plus 1 plus y squared plus 2y plus 1. Okay. Nothing I can really see to do right away. I guess we can bring everything over to one side. Okay, so 4x squared minus the x squared, so we'll get 3x squared on one side minus 2x plus 3y squared minus 2y and minus 2 is equal to 0. Right, the x squareds come over, the y squared comes over, minus 2x minus 2y, and the two ones become negative 1. Okay. So, okay. I don't know whether or not I want to keep these integers here or get rid of these 3's and divide everything by 3. I think I'm going to divide through by 3. Because I like having a leading term with my squares to be 1. So, it doesn't change the overall equation, so the relationship between x and y is still going to be the same. Okay. So when I see something like this, I have sort of two options. Okay, when I have something like this, so I got x squared minus 2/3 x plus y squared minus 2/3 y minus 2/3. When I see something like that, I have two options, usually on a contest. One, I can treat it as a quadratic in x, and then all the y's become a constant. So we have x squared plus or minus 2/3 x plus, and then I have a constant term of y squared minus 2/3 y minus 2/3 is equal to 0. And then I could probably quadratic formula and get x in terms of y. So that wouldn't be bad. Another option, which we can use here, is we can sort of complete the squares on both sides, and we'll get something involving x squared plus something involving y squared is equal to some constant. And then we're looking at a circle or an ellipse. So either way will probably work fine. I think what I'm going to do is complete the squares. Will that be better? Let's just take a look here. We're going to get sort of two very similar looking squares here. So that's interesting. Well, let's see. If we were to complete the square, then we'd sort of have a circle of coordinates that x and y can both be on. Does that make sense? So as theta changes, dp gets sort of it moves around. So p should be moving around in correspondence to the changes in theta. So I guess if we have a circle of coordinates that x and y can be on, those represent the different possible p's based on theta. So yeah, it kind of makes sense, I guess, to treat it as though it's a circle of potential p coordinates. Plus, having something like y squared minus 2/3 y minus 2/3 under a square root sign, which you will if you treat this as a quadratic in x, that can get kind of messy. So I do try and avoid that when I can. So let's complete the square. So if I have x squared minus 2/3 x, I want it to look like x minus a squared. That's going to be x squared minus 2ax plus a squared. So my minus 2/3 is minus 2a, so a is going to be 1/3. So I need to add on 1/3 squared, which is 1/9. So x squared minus 2/3 x plus y squared minus 2/3 y minus 2/3 equals 0. We'll add and subtract. So we'll add 1/9 and subtract 1/9. Then y squared minus 2/3 y plus 1/9 minus 1/9. And then overall we subtract off 2/3 as well. Okay, well then that simplifies to x minus 1/3 squared plus y minus 1/3 squared. Minus 1/9 minus 1/9 minus 2/3 equals 0. So I'm just pausing because, all right, well, we'll finish up what this square is, and then I'll state my hesitation by redrawing my picture. I feel like something has gone wrong, and I'll explain why. So x minus 1/3 squared plus y minus 1/3 squared is equal to, so 2/3 plus 1/9 plus 1/9, well, that's 6/9 plus 1/9 plus 1/9, so that's 8/9. So P lies on a circle centered at 1/3, 1/3, with radius square root of 8/9, so that's 2/3 root 2. Okay. Now the reason I'm hesitant for that is because based on our picture, all right, if I just redraw our picture right here, just very briefly, so I have P here, Q here, we have P here. So we're saying that P lies on a circle, but our center was right here. So P should definitely almost always be to the left. At least that's the way the picture makes it look. Whereas the center of our circle is sort of right here, 1/3, 1/3. I would rather it be something like 1/3, negative 1/3, or something like that. That would at least make more sense to me. So let's go back and double check and see whether or not our circles make sense and whether or not we've made a mistake somewhere. So I know dp, that formula worked out fine. And p, that formula also worked out fine. So that's great. So we rearranged just fine. Dividing by 3 didn't hurt. We completed the square just fine. I guess it works out. It doesn't seem like the center of that circle should be over there. Plus 2/3 root 2, that sort of seems kind of big. I guess that would also mean that P could coincide up here. And Q would have to be down here. No, I guess that makes sense. Because if D and Q coincide and P and A coincide, or P and B coincide, yeah, no, okay, all right, I'm convinced. All right, I'll stop worrying about this. So I guess that is big enough. So P lies on a nice big circle here. Okay, incidentally, I have 2/3 left to complete this 1, and 2/3 to go up. So that's how I knew 2/3 root 2 is going to pass through 1, 1. So yeah, okay, that makes sense. That makes sense. All right, so we have a circle here, and that represents the possible points of P. Now, does that actually help us in any way? Well, I think it probably would. So let's redraw our picture, but without any of the lines. Let's just draw that circle. And so we have our line here from D to P. Here's an example. Here, P could be here. Or maybe P could be all the way over here. It'd be outside of the square, so that's not helpful. Or there's another P value, or it could go right through to here. So we have a whole bunch of P values. So each position of P on this circle gives us a particular angle between A, D, and P. So we want the smallest angle. So the smallest angle is going to be I want to say closest to AD, but I don't think that quite is what I want. Let's redraw our picture. What do I want? What do I want here? So here's my circle. So let's pick a value P. So maybe it was here. So we have sort of this line going through here. So maybe, yeah, that looks good. So here's our P value. I know I can get a smaller angle by moving further over sort of on the circle, because we have more space left in the circle to cut through. So I guess until I think a tangent point is what we're looking for. So let's phrase that properly. Make it smaller by, how am I going to explain this here? Because that's the key. I want to explain why I need to eventually get a tangent. So the less area of the circle is on the side of DP closest to, what was that, to A. So to minimize, not minimize, we want to minimize this area, we need dp to be tangent. Just thinking about it, do I even know how to get a tangent here and turn that into a corresponding angle? Regardless, the reasoning is sound. So we definitely do need a tangent. Okay. So that's great. So we need to find a tangent for this circle. So let's draw our picture again. So we have our circle, we have it at the center. So we need dp to be tangent. Oh, that tangent very nearly worked out. And one of the nice things we know is that we can drop a radius. And tangents meet circle. When you drop a radius to the tangent point, you get a right angle. So we actually get ourselves a right angle triangle. And we know some of these lengths here. We know that this is going to be 2/3 root 2. And thanks to knowing what the coordinate of D is and the coordinate of our center, we should be able to get the hypotenuse, and then we will get the length of dp. And once we have the length of dp, we should probably, because we'll also be able to figure out the coordinates of p most likely, we should be able to get the angle theta. Let's call the center of the circle O. No, not O, let's call it R. So we'll let that be the center of the circle. So we'll suppose P at xy is tangent to the circle, then dpr is right angled at P. So PR is the radius, which is 2/3 root 2. dr is, well, we can use that distance formula. Square root of 4/3 squared plus 4/3 squared. So that's going to be 4/3 root 2. Oh, that's cool. I do believe we have a 30, 60, 90 triangle on our hands. 4/3 root 2 there. And so dp, when we squared that, we did this calculation a little while ago, is x plus 1 squared plus y plus 1 squared. But dp is also dr squared minus pr squared. So that's 8/9. And this one here is 32/9. That's 24 over 9. So, So x plus 1 squared plus y plus 1 squared is equal to 24 over 9. How does that help me exactly? I haven't a clue as to why that doesn't give me an x or a particular y. So that's not good. That just gives me a brand new circle. Ooh, geez. Do I actually need to figure out x and y to get theta? Well, let's just add in right here for a moment. That's got to be 60 and that's got to be 30. So this is 4/3 root 2. Trying to figure out how I can get x and y. Well, I suppose because PR is perpendicular to DP, their slopes have to be negative reciprocals. PR is perpendicular. So the slopes are negative reciprocals. Reciprocals. Pro or pre? Well, it doesn't matter. Negative reciprocals. So that means rise over run. So rise over run has got to be the negative reciprocal of the other rise over run. Okay, so y plus 1 over x plus 1, so maybe we'll get a nice little ratio between those two guys. That'll be 1/3 x, or 1/3 minus x. Over y minus 1/3, and we can multiply these out. So y plus 1, y minus 1/3 is equal to 1/3 minus x, x plus 1. Don't really see this helping me much. So plus 2/3 y minus 1/3. And that's going to be 1/3 minus 2/3 x minus x squared. I don't really see this helping at all. Is there something easier I could be doing? So now x plus 1 squared is plus y plus 1 squared should be 24 over 9. I was hoping to get something more substantial, like get an x and a y here. Well, I had another calculation for dt a while ago. It was 4x squared plus 4y squared. So that would mean x squared plus y squared is 6 over 9. So yeah, actually, I think I'll try that instead. So 24 over 9 is dp squared, but that's also pq squared. This is 4x squared plus 4y squared. So x squared plus y squared is equal to 6 over 9. So x plus 1 squared plus y plus 1 squared is equal to 24 over 9. And that's x squared plus 2x plus 1 plus y squared plus 2y plus 1 is 24 over 9. And I can substitute in x squared plus y squared. So that's 6 over 9 plus 2x plus 2y plus 2 is equal to 24 over 9. Divide everything by 2, so we get 3/9 plus x plus y plus 1 is equal to 12 over 9. Those two will cancel out and give me 9 over 9, which is just 1. So x plus y is equal to 0, I think. Okay, so x plus y is equal to 0, or y is equal to negative x, and now I can substitute that in. So 4x squared plus 4y squared was equal to 24 over 9. But since y is equal to x, then that's 4x squared as well, 24 over 9. So we have 8x squared is 24 over 9. X squared is going to be 3 over 9, which is 1/3. So x is plus or minus 1 over the square root of 3. And y is minus or plus the same thing. So when x is the plus 1 over root 3, then y is the minus 1 over root 3. And this makes sense. Now we have two pairs of points, so we have two tangent points, and that makes sense to us. And that's good. We were trying to find tangent points from a given exterior point D, and it makes sense that it would have two tangent points, one on either side, and we now have our two tangent points. 1 over root 3 and negative 1 over root 3, and then our other tangent point is negative 1 over root 3, 1 over root 3. So this is making sense. And now we can try and figure out theta from here. Okay. Now we want the particular pair xy that happen to be closest to A. So we want the tangent that's closest to A, although there's a giant degree of symmetry in here, so I imagine we could make the theta calculation using either one, and we'd be pretty okay. So that is P at, well, A was negative 1 negative 1, 1, so we want negative 1 and 1/3. So that's theta here. Here's p at negative 1 root 3, 1 over root 3. And tangent of theta should be the, so here's our opposite, here's our hypotenuse, here's our adjacent, so we're going to use SOHCAHTOA. So the adjacent, because we're going down to negative 1, negative 1, so our opposite should be the absolute value of negative 1 minus negative 1 over root 3. And our adjacent should be 1 plus 1 over root 3. So tan sigma is opposite over adjacent. So the opposite we said was the absolute value of negative 1 minus 1 over root 3. So that's going to be root 3 plus 1 over root 3. All over the adjacent, which was 1 plus 1 over root 3. So that's I'm pretty sure this should actually be a minus 1 up here. Yeah, that gives a positive value, and that's 1 minus the distance we've already canceled. Okay, so that's good. So these root 3's are going to cancel one another out. And so we are looking for a tangent of an angle. So we know 0 is between theta and... did they want it in degrees? Let's check. Minimum possible value doesn't say it has to be degrees. I would go with whatever your calculator is defaulted to. So mine's defaulted to degrees. But we know theta has to be in that little corner, so it's got to be the corner angle there. And so, where are we here? So we want theta is arctan root 3 minus 1 over root 3 plus 1. Now, the amount of root 3's in here suggests to me that this is probably a very nice angle. So, you know, not quite as nice as, say, 30 or 60, but I could see it being like 72 or 54 or, you know, just another nice angle. So I'm grabbing out my calculator. And I'm entering this in. So I get the tangent of theta should be about 0.2679. So I'm going to arctan that. And I get exactly 15 degrees. So 15 degrees, or what is that? That's pi by 12 would be another way to say that. It all depends on which way your calculator is set up. Most calculators default to degrees, so that's what I'm putting it in. So 15 degrees, and that looks like an excellent answer. And because it was such a nice answer, it wasn't something weird like 17.98220101, something weird like that. 15 degrees, that suggests to me it should be the right answer. And we've shown all our steps there. We explained a little bit why we needed a tangent for that circle. We found that circle in the first place just by using the fact that dp and pq must be the same length. So we've come a long way in this question, and there were definitely some points where we didn't quite know what we were doing, but we persevered and we worked it all out. And well, that's too far. So yeah, not bad question. Certainly took us a while. It was a worthy question 10, as I've come to expect. Bit of a challenge. There was some I'd say some adventure on there. There were certainly a couple things we tried. I remember when I thought I was going to use that negative reciprocal thing. But it turns out the fact that dp and pq were equal gave us enough information to work out the x and y coordinates of our tangent points P. And from there we got our thetas just by using the SOHCAHTOA that we learned. So 15 degrees, and that's our final answer. And not a bad Euclid contest overall. I liked this one. If I had to pick out a standout question, I really liked 6A because there was some logic involved. Not a whole lot of math, but some logic involved, and I really liked that. 10 wasn't a bad question either, but I think I really liked 6A there. So that was the 2001 Euclid paper, again put out by the University of Waterloo, specifically created by some folks at the Center for Education in Mathematics and Computing. Their link will be in the description below, so you can try all sorts of contests. I'm going to move on. The next Euclid I'm going to be doing is the 2002. So if you liked this one, feel free to throw a like on the video. And of course, join me for the 2002 next time. I highly suggest that you go to the CEMC website, try the 2002 Euclid before watching. That way you can see where your weaknesses are and what videos you need to be paying attention to, and what concepts that I bring up that you might want to look into. So that's all for now. Thanks for watching, and I'll see you guys in the next video, whatever that may be.